Today I am giving the lecture on the topic Nonlinear Systems of Advanced Control Theory. Myself Manoj Kumar, St. Thomas College of Engineering and Technology, Chengalpattu. Module 5 can be divided into three. First part is the introduction to nonlinear systems, different types and characteristics. Second part is the describing function analysis and the derivation of some basic nonlinearities like a saturation, dead zone and a relay. The last part is the application of describing function for stability analysis. Here I am handling the first part of module 5. The basic difference between linear and a nonlinear system is that superposition theorem cannot be applied for nonlinear systems. To explain superposition theorem, consider a system with a transfer function g of s. If the input is x1 and output is y1, to the same system, if you are applying x2 as input, then output is y2. Next, we are applying x1 plus x2 as input. If the response we are getting is y1 plus y2, then we can say that the given system is linear. This is the superposition theorem. To verify the superposition theorem, consider a system y is equal to ax plus b dx by dt. We know that for x is equal to x1 plus x2, if y is equal to y1 plus y2, the system is linear. For getting this, put x is equal to x1 and x2. The corresponding outputs are y1 and y2. Then substitute x is equal to x1 plus x2. The response is y1 plus y2. So we can confirm that the given system is linear using superposition theorem. Introduction to nonlinear systems. Consider a spring. When a spring is loading, it gets extended. As the load is increasing, the force displacement curve is linear within the working range. When the load is increasing beyond this maximum working range, the spring starts yielding and becomes permanently deformed. That is, the spring behaves linearly over its working range, and beyond this range, it acts as nonlinear. So, in all control systems, there will be always some nonlinearity due to saturation, dead zone, friction, backlash, inertia, etc. The effect of all these nonlinear components can be avoided by restricting the operation of the component over a limited range, and up to this limited range the system is acting as a linear, and after that the system working as a nonlinear. Thus the characteristics of all these components may be considered as linear up to some working range, and after this range this system working as nonlinear. Next we can discuss different nonlinearities. Nonlinearities can be classified into two, incidental and intentional nonlinearities. So what is incidental means? These type of nonlinearities are inherently present in the system. That is, saturation, dead zone, friction, backlash, etc. are the examples of incidental nonlinearities. The next one is intentional nonlinearity. These are deliberately inserted in the system to modify system characteristics. Example is the relay. Next we can discuss one by one. Then first is the saturation. In the saturation nonlinearity, the output is proportional to input up to a particular value, and after this value, when input is increasing, output remains constant. So up to that particular value, the operation is linear, and after that the output is constant. Next one is the dead zone. The dead zone is a region in which the output is 0 for a given input. If the input amplitude is less than some small value, then there will be no output. The region in which the output is 0 is called as dead zone. When the input is increased beyond this dead zone value, the output is linear. The figure shows, first figure is a dead zone and next one is a dead zone with saturation. Third one is a relays. Relays are commonly used in industry for controlling large amount of power to a circuit by using a very small amount of power for operating the relay energizing coil. The relays are thus very large scale power amplifiers. The input output characteristics of the relays can be of different types depending on the nature of the relay. There are so many types of relays are available now. The first one is the ideal relay. In ideal relay, the output switches between plus M or minus M depending on whether the input is positive or negative. If the input is positive, it switches to plus M, and negative, it switches to minus M. Next is relay with a dead zone. In this type of relay, when input is greater than A, the output switches to plus M for a positive cycle, and for a negative cycle it switches to minus M. So the region in between A and minus A is a dead zone. The next one is the relay with hysteresis. In this type of nonlinearity, there exists a hysteresis loop when output rising one curve for increasing values of input, and when we are decreasing the input value, the output rising to another curve. So this arrows shows the directions for increasing and decreasing values of inputs. The overall system behaves like a hysteresis loop. Next is different types of springs. I have already explained about springs, and input output characteristics will be different for different types of springs. Normally there are three types of springs: linear, hard and soft springs. In linear spring, the input output relationship is linear, and then we can explain with a mathematical relation f of t is equal to k into x of t, where k is the compliance of the spring and f of t is the applied force and x of t is the displacement. And in the case of hard spring, if the elastic limit is exceeded, the input output characteristics can be explained as f of t is equal to k1 x of t plus k2 x cube t, and now the relation becomes nonlinear. And similarly for soft spring, the input output can be given by f of t is equal to k1 x of t minus k3 x cube t. The figure shows the input output characteristics of all springs. In the middle we can see the linear spring. On up is a hard spring, on down is a soft spring. We can see that the sign is positive for hard spring and negative for soft spring. Next is the friction. This friction exists in any system when there is relative motion between contacting surfaces. The different types of frictions are viscous friction, Coulomb friction and stiction. First of all, viscous friction, and this type of friction is linear, and the frictional force is proportional to relative velocity of the sliding surfaces. So the input output relation is shown in the graph. The curve is linear. The Coulomb friction and stiction are nonlinear frictions. The Coulomb friction offers a constant retarding force only when the motion is initiating. Due to interlocking of surface irregularities, more force is required to move an object from rest than to maintain it in motion, so which is the stiction. Hence, the stiction force is always greater than Coulomb friction. In actual practice, the frictional force gradually decreases with the velocity and changes over to Coulomb friction at low velocities, which is shown in the figure.